This is lesson 6.3, solving multi-step linear equations. Sometimes linear equations will have a variable that appears more than once, and it appears on both sides of the equation. So like this example here, we have a 2x term and a 4x term, and they exist on both sides of the equation. In order to solve for x, we need to collect like terms and combine them so we only have one variable. And to do that, we need to get them on the same side of the equation. So how do we solve equations with variables on both sides? The first step is to bring all of the variable terms to the same side of the equation by adding or subtracting their opposites. It doesn't matter if you bring them all to the left side or bring them all to the right side, just get them on the same side. Sometimes you might prefer one or the other based on if you want a positive or a negative, but it doesn't actually matter. So in this example up here, I could bring the 2x to this side, or I could bring the 4x to this side. Just get them on the same side. What I mean by adding or subtracting their opposites is if I wanted to get 2x over here, I would have to subtract 2x on this side and then subtract 2x on this side. So it's the same idea that we've been working with so far, we just also have a variable. Because if we have 2x and we subtract 2x, those go away. And since we do it to one side of the equation, we have to do it to the other as well. So now we have our 4x term and our 2x term on the same side, and the sign has changed because we've brought it to the other side of the equation. Once they're on the same side, you're going to collect your like terms, which we know how to do, and then you'll just solve for the variable like normal. A couple examples. So in this one, we have to bring all the x terms to the same side of the equation. Again, it doesn't matter which side, and I've underlined in green which ones we're talking about. So I'll bring the 5x to the other side because why not? It'll make it positive because we'll do the opposite sign, and it's usually easier to work with positives. So to move the negative 5x to the other side, we're going to add 5x on both sides of the equation. Whatever we do to one side of the equation, we have to do to the other side of the equation. So then these two cancel out. You have 5x and then you take it away. So we're left with just 6 on that side. And now we have this positive 5x on the right side. Now that the variables are on the same side of the equation, we can combine our like terms. 3x plus 5x gives us 8x, which we have here. And then we just solve like normal. We need to get x on its own. So first we'll add 2 to both sides to get rid of that. Then we've got 8 equals 8x. So the final step would be to divide both sides by 8 to get x on its own. So your answer is 1. Another example here, we've got some fractions. So again, it doesn't matter which side you bring all the variables to. In this case, it kind of makes sense to bring this term over to the other side so that because if you do it the other way, if I bring this over here, then I'll have nothing left on that side. I'll just be left with 0, and that can be a bit confusing. So I'll bring the 1/2x over to the other side, and I'll do that by subtracting both sides by negative 1/2x, the opposite of this. So I'm just left with 3/2 here, and I've got my minus 1/2x on the other side. So my x's are on the same side. Now I can combine and collect my like terms. But in order to do that, because we have fractions here, we need to find a common denominator first in order to combine these coefficients. We have 2/3 x, we're subtracting 1/2x. We need to know what 2/3 minus 1/2 is to know how many x's we have left. And in order to do that, we need a common denominator. So that's what I did in this step here. The common denominator would be 6. So I multiplied this fraction by 2/2 and this one by 3/3. Now that they have the same denominator, if we have 4/6 minus 3/6, that leaves us with 1/6. We've got 1/6x. Then we solve like normal. To get x on its own, we're going to divide by whatever number it's being multiplied by, which is 1/6. So we're dividing by it. We'll do the same on the other side. This gets us x on its own. And again, we have some fractions to deal with. We have 3/2 divided by 1/6. When we're dividing fractions, we change it to multiplication and flip the second fraction. So 3 by 6 is 18, 2 by 1 is 2, and then we reduce to 9. If that last little bit was confusing, another way you can think about it from this step is just multiply by 6. Because the opposite of multiplying by 1/6 is multiplying by 6. In other words, if we have this, we multiply by this, we get 6/6, which is just 1. And then so that's essentially gone away because then we have our 1x. So maybe that makes it more confusing. If so, just ignore what I just said. But the opposite, if you have a fraction out front, you can just multiply by that denominator and they will cancel out. This example, we have a lot of n terms. We need to collect the like terms on the same side. So there's 3 on this side and only 1 on the other. So it makes sense to bring this one over here. We'll do that by adding 5n to both sides. So then we've just got 13 over here now, and we have all our terms here that will combine together by adding or subtracting the coefficients. So -2 plus 4 minus 3 plus 5 gets us to 4n. So this step to this step, it's way simpler once we've combined all our like terms. Now we just have one variable and we can solve like usual. We'll bring the 11 to the other side. We'll subtract both sides by 11. Then we'll divide both sides by 4. And we'll fully reduce our fraction to get 1/2. Couple more examples where we're going to bring everything together that we've learned in chapter 6. It all builds on each other. So this one we want to solve and check. The first step would be to get rid of these brackets by multiplying in. So this is like in the 6.2 lesson when we have brackets. How do we deal with that? Like if we look at this, the first thing I notice when looking at this equation is we have an x here and we have an x here. We know we need to combine those together in order to solve for a single x. But how do we do that when this x is locked in with those brackets? We can't do anything until we get rid of those brackets. And remember when we were learning in 6.2, there's 2 methods to get rid of brackets. Either multiply the number on the outside into the brackets, which is what I do here, or divide both sides by whatever number's on the outside. Either of those are fine. Just know that if you did the division method, you would divide this whole thing by 2, which if you're comfortable with fractions, go for it, but that could be a little confusing. You'll have 30 over 2 minus 4x over 2. That's fine too. But I did the distributive method. So this became 2 times x plus 2 times 5. And then that multiplication is easy. 2x plus 10 equals 30 minus 4x. So now that I've gotten rid of the brackets, this looks similar to questions we did above, where we want to get our x's on the same side so we can combine them. That's exactly what step 2 is. Bring variables to the same side to combine. So I brought this negative 4x over by adding 4x to both sides. So it's gone from here because I added 4x and then I inserted here, positive 4x. And those combine together to give me 6x. The last step is to isolate for the variable by using your opposite operations, just like in our 6.1. So I'll subtract 10 on both sides and then divide both sides by 6 to get an answer of 10 over 3. This question has told us to solve and check our work. So let's do another reminder of how to check our work. We do this by substituting the answer that we got, in this case 10 over 3, into the original question. So we'll set up our left side and our right side of the equation. The original left side of our equation was here. This was an x, and I just replaced it with what I just found, which was 10 over 3. So we're essentially testing if x can be 10 over 3. If x is 10 over 3, do our sides equal each other? So we'll do a bit of math here. 5 becomes 15 over 3 so that they have a common denominator. Then I combine the numerators. Whoops. I combine the numerators. 10 plus 15 is 25 over 3. Do my final multiplication, I get 50 over 3. So no, you're not trying to see if this equals what you just found. That's irrelevant. What we're trying to see is if left side equals right side. So I'll do the same with the right side here. This is an original question. It was 30 minus 4x. So I write it as 30 minus 4 times whatever x used to be. That used to be an x, and I'm going to test if it's going to be 10 over 3. So I replace x with my answer. 4 times 10 over 3 is 40 over 3. I find a common denominator, and I find that, yes, my answers do match. My left side equals right side. They're both 50 over 3. So we know that we've done this question correctly, and that 10 over 3 is a valid answer for this equation. 2 more examples, then we are finished. These are just, I wanted to do them because you might see some of these in your workbook, and it looks a little confusing at first, but it's the same idea. So in this first example, we've got 2 fractions. What do we do first? The 4m minus 5 and the 6m plus 4, those are locked in with that big denominator. They're all being divided by 3. We can't really do anything with it until we get rid of that 3. So if I multiply both sides by 3, then those big fractions cancel out. And instantly, my equation's a lot easier to work with. I don't have any fractions left over because I've removed them by multiplying by 3. Then I solve like normal. I bring my 4m to the other side. I combine the like terms together, and I solve for m. In this question, there's a ton of fractions going on, which can be overwhelming and confusing. So how can we get rid of them? Where do we even start? If you notice, the numbers 3, 4, 2, and 6 all go into 12. So why don't we just make our life easier and get rid of all these fractions if we multiply every single thing by 12? That's what I did in this step here. I multiplied every single term by 12, and then it works out nicely that all the fractions disappear because 12 is divisible by each of those denominators. Once the fractions are gone, this is a much easier equation to work with than the original question. Then we just, again, bring the x's to the same side, combine your like terms, do your opposite operations until you get x on its own. So that is kind of a combination for all of chapter 6 of how we solve linear equations, how we isolate for variables by doing opposite operations, removing brackets, and collecting like